Let's take a look at sequences as functions. So the first thing I'd like you to do is on page 22 and on page 24, this is your notes packet, I would like you to read and complete numbers 1 through 4 on both of those pages. Since you've had an opportunity to review sequences a little bit, hopefully you'll be able to breeze right through these. Pause the video here and take a look at page 22, 1 through 4, and page 24, 1 through 4. So if you're back now with me, we'll just go over these quickly. Remember, an arithmetic sequence increases or decreases at a constant rate. It's called the common difference. And if we were to be given the sequence 12, 15, 18, 21, our common difference would be 3. In order to write an explicit formula for that, we would take a sub 1, which is 12, and add our common difference, which is 3, n minus 1 times. To simplify that, I would just get a sub n equals 3n plus 9. So what type of function would that be? Well, if we think about it and we think of a sub n as our dependent variable and n is our independent variable, then this would be a linear function. And we could actually write our sequence in function notation. So down in this text box at the bottom, you see a description of an arithmetic sequence as a linear function where n is the independent variable and a sub n is the dependent variable. And your common difference, once you've simplified that expression, is the slope. So we can write that in two different ways. And the thing to keep in mind here is that, remember, n is the number of the place in line of that term. For instance, a sub 3 is 18 because 18 is the third place in line. Our domain can only be the counting numbers, and the range would be the actual terms of the sequence. So on a graph, we would represent this as a discrete function. Taking a look at some of these arithmetic sequences on page 23, if we look at the seating example here, there are 20 seats in the first row, and then 22 and 24, etc. So our a sub 1 in this case would be the first term, which is 20, and the common difference would be 2. And then this example basically walks you through how to convert the information into a function. This is my general form for an arithmetic sequence, the explicit formula. And in this case, my a sub 1 is 20, my common difference is 2, and when I simplify that, I get 18 plus 2n, and then I can just write that into function notation here. So f of n equals, you could write it 2n plus 18 or 18 plus 2n. And then if we were to graph that, again, the dotted line is just for demonstration purposes. You wouldn't actually graph that line because these are discrete values. Okay, so take a look at the first practice question. Pause here and come back and we'll go over it. All right, in this case, good for you, Sarah. She's learning to knit, and the scarf she's knitting starts at 13 inches. Today it measures 18 inches. Yesterday it was 15.5. So if I think about that, my common difference is going to be 2.5, and when I simplify that, I get 2.5n plus 10.5. The next example, there's just one little thing I want to discuss before you start. Now, there's two different ways to look at writing a formula for the sequences. I like to think of it the common sense way, and I'm going to show you a video that talks about the other way. But for me, starting with 64 ounces, that is really, to me, that's a sub 0. I haven't poured anything yet. That's my, before I do anything, that's where I'm starting. Once I have the first pour, then I will have less water in my pitcher. So this example tells us that after you've filled 8 cups, the pitcher is empty. Therefore, we can figure out how many ounces are in each cup, and then we can subtract those number of ounces per pour. I would think of a sub 0 as 64, and a sub 1 would be the number of ounces that I pour on the first time I pour a cup. Okay, pause here and see what you can do with this example. All right, I did list my first couple of terms. I started with 64 as a sub 0, and so my first term was 56 because since there are 8 cups and there was 64 ounces that we depleted after filling the 8 cups, each cup has 8 ounces. And then my common difference would be 8 and 64 minus 8n. So obviously this works out. If I plug in the 8 cups, I would get 0 ounces left, so that works. When you're graphing these, be sure to label your axes. So I have ounces on the f of n axis and cups on the n axis, and they have a sub n here, so either one. And as you can see, this is a linear function. Great, so let's move on to the geometric sequences. We are given the sequence 21, 63, 189, so our common ratio is 3. And if I write an explicit formula for this, we say a sub n equals a sub 1 times 3 to the n minus 1. And the general form for a geometric sequence is a, my original amount, times 1 plus or minus the rate. Remember, this would be my growth or decay factor to the nth power. These are basically the same format. So if I write the first one in function notation, it would just look like that. And again, n is going to be the place of each term, so it's going to be a counting number domain in a discrete function. The first example here is a very famous story about the number of grains of rice, and it kind of is similar to our penny problem that we did when we did exponential graphs. Courtier presents the Indian king with a beautiful handmade chessboard, and the king asked what he would like in return. The courtier surprised the king by asking for 1 grain of rice on the first square, 2 on the second, 4 on the third, etc. The king readily agreed and asked for the rice to be brought. How many grains of rice does the king have to put on the last square? So the first thing they want you to do is write a function. My common ratio, since I'm doubling each time, my common ratio is going to be 2. My function will be what I'm starting with, which is 1 times 2 to the n minus 1. And they want us to graph this function for the domain. So I think what you should do first is create a table with n and f of n for the domain 1 through 8. And then notice I did show you here how you should be labeling this. You should have f of n on the y-axis, n on the x-axis. Label your grains of rice here and the number of the squares here on the x-axis, and then you can scale this however you'd like. I think I used 4 blocks for 25. Okay, why don't you pause here, create the table, create the graph, and come back and check. All right, here's my table. I have each of the terms listed and the appropriate range for them. I graphed this. Again, it was discrete. It is exponential. I don't have this labeled here, but I used 2 blocks for 1. That's 2, 3, 4, 5, 6, 7, and 8. If we were to plug in f of 64 to this, I get 1 times 2 to the 63rd, which is an incredible number. This is coincidentally the same number of brackets that are possible in the March Madness tournament. So if you ever wanted to know, that's the number of possible brackets that are out there. Example 2. Before we do this, I'm going to show you this quick video. It discusses what I was talking about before regarding the common sense method and the formula method, and hopefully this will work.
What we're going to focus on in this particular problem is a bouncing ball. What will show up is a lot of different issues that will show up in a lot of different types of word problems. So it's applicable to a lot of word problems that we're going to get into in geometric sequences in the series. This problem says a ball bounces to 65% of its previous height after each bounce. If the ball is dropped from 15 meters, determine the first term, the common ratio, and Tn, so the general formula. The first term here is the height that it's dropped from, so T1 is equivalent to 15. The common ratio here is 0.65 because every bounce it's reached.
Now again, this is not how I do it, and he will explain this later. I would consider this to be T sub 0, and I would put T1 as 65% of 15. But he clarifies that in a couple minutes, so just hang on for a second and go with it.
65% of its previous height. So the general formula would be that T1 is equivalent to 15 times the common ratio to n minus 1. So if you look at this next problem, the extension says, what height does the ball reach after 9 bounces? So this is a general term problem. So we're not finding the sum of all the bounces. We're finding after 9 heights, so here's 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 bounces, what's the height of the ball? And it says to the nearest tenth of a centimeter. There's a couple things we need to be careful of. You could either use the common sense method or the formula method. If you're going to use the formula method, what you have to be aware of is that term 1, which is 15, is actually before 1 bounce. I'll show you why this is important in a second. Term 2, if you wanted to find it out, it would be 15 times 0.65, so 65% of that height would be 9.75. That is after 1 bounce. And if you look at the next part, term 3, for example, would be after 2 bounces. So what you'll notice here is that term 9 is actually not after 9 bounces. If term 3 is after 2 bounces, then it's actually going to be term 10 that's after 9 bounces. So just be careful about that if you're going to use the formula. So in this particular case, term 10 is what we're solving for, not term 9, even though it's after 9 bounces. So if we use the general formula, it would be that the term, or the value of that term, is equivalent to 15 times 0.65 to n, which is 10 minus 1, so that is 15 times 0.65 to the 9th. So in this particular case, solve what it is, 0.65 to the power of 9, and then times 15, and that height is 0.3106, so 0.3106, and that would be, if I times that by 100, because it wants it in centimeters, and we're in meters at the moment, that would be 31.1 centimeters after 9 bounces. The common sense method would say if you don't use the formula, it would be 9 common ratios later that would be after 9 bounces. So the exponent here would be 9. You could have jumped straight to that step. The next problem says,
Okay, we don't need to go to the next problem, but I did want to highlight this. I'm a common sense person. I don't like to have to make adjustments at the end. I mean, other than the meters to centimeters, which is actually very important, but I don't like to have to be thinking about this all the time. It's easier for me to think about it at the beginning and say, I'm going to let that be t sub 0, and then t sub 1 is after the first bounce, and then I know that when I plug in 9 here, I've gotten the right answer. I don't have to adjust accordingly. So just be aware of that depending on how you set it up. So knowing that, I would like you to take a look at this example too. And I'm going to do it the common sense method. You're welcome to do it however you would like, but I will give the answers will be the same in the long run, but you'll have to adjust yours if you're using t sub 1 equals 8. So pause here and take a look at example 2. Alrighty, I got f of n equals 6.4 times 8 to the n minus 1 because this should be a 0.8, sorry about that. I use t sub 1 at 6.4, which is 80% of the 8 feet. Here's my bounce. The first bounce is 6.4, second bounce 5.12, third bounce, fourth bounce, fifth bounce. The fifth bounce is 2.62144, so that's approximately 2.6 feet. And if I were to graph this, notice I have my labels, and I can just show that graph here. Great, that's basically sequences as functions. I will have some practice noted for you that you can work on over the next couple of days. Have a great day, everybody. Talk to you soon.